On that too. Okay, science time, physical science time. Thanks for giving me an obstacle to step over, Mason. Let's do this one in brown. Today we're talking about calculating motion. Yeah, like locomotion. That is so true. Like locomotion. What is motion in general? Moving. What else? Driving is a type of motion. Give me some more types of motion. What are some other things that move? Flying. Yes, this is maybe kind of elementary school. Swimming. Yes, very good. Okay, now how do you think in science motion is measured? I hope you know because you did it yesterday. How do you measure motion? Okay, with time. So first of all, we have it definitely has time because you noticed in your lab, I hope, that when someone locomoted, when someone moved faster, did it take more or less time for them to cover that certain?
10 meters.
Okay, 10 meters, which is a distance. Good. So the way that we measure motion involves distance and time. We call it in science a rate. It's a rate. The way that we measure motion involves distance and time, and we call it a rate. Where else have you heard the word rate before? I'm trying to think of a way that this relates to like ratings, like when you rate a movie or rate food, but I can't really think of how those things are connected. Where else do you hear about rates? Math, yeah. If I tell you that the rates of gas have gone up, what does that probably mean? The gas prices have gone up. The amount, in effect, that you pay per gallon of gas. So when we use rates in math, we're often, or at least in science, we're often using the word per. So like miles per hour. Or in your case of the lab yesterday, what was the unit you used? You came up with? Well, you had a distance measured in. No, a distance measured in meters, yes, whether it was 10 or not is not what I'm asking right now, but a distance measured in meters, and you then did what math to it? Which of the 4 basic math operations did you do to that distance? Try one more time. Divided by what? To get the speed in your lab. Yeah, you divided it by the speed. So that's how we calculate. That's one of the ways we calculate motion. We say that speed equals distance over time. We write this as v equals lowercase d over lowercase t. Lowercase v equals lowercase d over lowercase t. Sometimes we might write it as s equals d over t if we're trying to be very simplistic. Where d is distance and t is time. In the SI, how do we measure distance? What is the base unit of distance in the SI? You've already said it. Meters. And the base unit of time in the SI? Seconds. And so if we're dividing meters by second, our base unit for speed is going to be meters per second. Meters per second, because it's a rate. It's a rate comparing distance and time. How do we know if something is moving? Motion is, okay, so if it moves, I'll do like the lady yesterday. Close your eyes. Everyone close your eyes. Everyone close your eyes. Do it now. Stop typing, or I guess you can keep typing as long as you have to have your eyes open. Tristan, close your eyes. Okay, wait, oh, sorry. Open your eyes again for a second. Look at me, look at me, look at me. Look at your boy. Look, Mason. Look with your eyes. Do you see me? Now close them. Everyone close them. Everyone close them. I'm going to sneak. Now open your eyes again. Look, I'm somewhere different. Now, the point is, you didn't see me in the process of motion, right? But you saw that my what changed? Position. Yeah, motion is change in position. That's what it is. And how do you know my position changed? Well, what if we were in that spooky Squidward land from the Squidward episode where he like breaks his mind and he goes to all white everything. Do you remember that one? That is the scariest episode of SpongeBob. Do you know what I'm talking about?
Yes. No, sure.
Okay, well imagine that we were in a totally white room and it was just me and I did that same thing. You closed your eyes and then I did the same thing. Would you be able to tell that I moved?
No.
Probably not, because you have to have something to compare it to, which we call a reference point. Reference point.
Unless you're behind me, then I'm probably.
Reference point. Yeah, and I wasn't trying to complicate it, Mason, but we would also have to assume that like you were incapable of judging your own position relative to me. But reference point is a, well, I guess we could just say point, which we compare to the object. That is one of the worst definitions I have ever done. But we have to talk about motion in relative terms, because motion is relative. All motion is as it compares to something else, as it compares to a reference point. All motion is as it compares to a reference point. All motion is as it compares to a reference point. Your book calls that a frame of reference, but all motion is as it compares to a reference point. If we were to specifically talk about the direction in which something's traveling, we now call that, does anyone know from your vocab, what do we call it when we also talk about the specific direction something travels? Has a cooler word, yeah, say it. Velocity. Velocity also includes direction. Sometimes we say it includes displacement. As opposed to distance, it includes displacement. Not just how far something went, but how far something went in a certain direction. Displacement is how far something went compared to its starting point. To describe displacement, the way we often do it is, if I do this, have I moved? Yeah. But am I displaced from my original? No. My distance I traveled was maybe 2 meters. 1 meter that way, 1 meter back this way. I traveled 2 meters, that's my distance, but my displacement is 0. I haven't moved from where I started. And if we divide that instead by time, we get velocity. Velocity equals displacement. Oops, why did I draw my D backwards? What is going on? Something must be in my coffee. Probably that wasp. Displacement over time. Again, displacement, though, is measured in meters. Time is measured in seconds. Velocity, then, is measured in meters per second. So it's still measured in meters per second, but it has a specific direction. One of the very good questions on your chapter review says, why do highways not have a velocity limit? It has a speed limit, but why does it not have a velocity limit? What's the difference between speed and velocity? Direction also. Okay. So why do highways not have a velocity limit? Yeah, because you can go both directions on the highway. Now, if you think about the one-way streets like in Chadron, that kind of is a velocity limit. This certain speed, right, 20 miles an hour, but only this way. That's a velocity limit. Okay, next. What if, so we say that motion is a change in position. Motion is a change in position. What if the motion itself is changing? Here's another drawback of having my desk all the way over there. I can't get to my science drawer, which is locked away. Let me spend a long time displacing myself over to the science drawer and getting a ball out. Which kind of ball should we use today? Tennis. That's the one that's on top, so tennis ball it is. Back over to the discussion area. Check this out. Check this out.
May I have Zach, Tristan, and Mason whenever you're done?
Okay.
Class.
Yeah. Yep. I'll send them up where we're
Sorry
working.
to interrupt.
That's okay. Okay. So I have this ball. This little boy is called tennis ball. I watched a video about how tennis balls are made. It's kind of interesting, but you can. I guess if you're watching this, you're watching it on YouTube, so you can search YouTube for how tennis balls are made to kill some time. before you die. This is a tennis ball, and if I drop it, I want you to watch its motion. So, first of all, right now, is it moving?
No.
Well, hold on. Is it moving? I mean, I'm wiggling it for one thing, but also, is it moving? Like, even if I hold it so still, in what frame of reference is it moving?
Shaking violently.
I'm not shaking violently. Pretend I'm holding it completely still, even if I were shaking violently. In what frame of reference, relative to what, is it moving? Is it moving relative to Earth? Relative to the sun, it is moving. Or maybe relative to the center of the Earth, it is moving, right? Relative to a car on the highway, I see a car going down West Ash Road right now. It is moving relative to that. But in our frame of reference, the usual frame of reference, if we don't specify another one, our reference point is the ground. So usually if we say something's not moving, we mean relative to the ground. But anyway, is it moving right now? No. But right now, is it moving? Yeah. Okay, so it was moving at that point. But not only is it moving, right? It's not like when I drop it, it goes at a certain speed, but it's also getting faster and faster. Do you notice that? What do we call that? Does anyone know? Yeah. Change in motion. I want you to learn this definition specifically. Change in motion is acceleration. If I drop it again, how is its motion changing? There are three ways motion can change. How is its motion changing if I drop it? Think only about the drop at this point. How is its motion changing? Okay, no, only the drop. How is its motion changing? It's going faster and faster down, right? So speeding up is one. But then, after it hits, boink. Now, as it comes back up, this is supposed to be slow-mo. As it comes back up, what's it doing? Slowing down. So that's another way that motion can change. And right when it hits, what does it do? Right now it's moving down, and then it switches to moving up. So that's another way that motion can change. It's another kind of acceleration. What do we call that one? Changing what? Direction. Yeah, good job. Change in motion is acceleration. We calculate it in this way. Acceleration equals final velocity minus initial velocity over time. Sometimes we say acceleration equals delta v over t. Just based on what I've done there and based on the definition, can you tell me what delta might mean in science? This is very important that you know this. But what might delta mean in science based on this definition and based on the equation? So we have acceleration is final velocity minus initial velocity. And down here we've changed that to acceleration is delta velocity. Yeah. In science and in math, as far as I know, the capital Greek letter delta, which just looks like a triangle, is change in. Change in whatever comes next. Changed in this case, change in velocity. Anytime motion changes, there is acceleration. Let me say it again. Anytime motion changes, there is acceleration. That's the definition of acceleration. Yeet. Did the motion of the tennis ball change? Yeah, at several points. So did it accelerate? Yeah, so accelerated at the very beginning, but watch yourself, because acceleration, as you use it in your daily life, or as the policeman uses it, just means speeding up. So accelerates at the beginning, sure, but does it accelerate when it hits Mason? Yeah, it does, because its motion changed. Now, this is what I'm trying to draw out of you, is there's a fundamental difference in the way that we use the word accelerate in our daily life, which just means speed up, but that's only a third of the ways that the scientist, and you're a scientist now, uses acceleration. It also accelerates when it slows down when it hits Mason, and it also accelerates when it changes direction when it hits him. Okay? Can you recognize, because there's going to be several questions on your test that a wicked student would think are trick questions, but are really trying to draw out, do you actually know this? Because a lot of people just think accelerate means speed up, but it don't. It means any change in motion. And then finally, we call a change in motion acceleration, but what causes a change in motion? What has to happen to an object to change its motion? What has to happen to it? You should kind of remember this from last year. What has to act on it? Let me phrase it that way. Be more specific. Newton's force. They're all his. Okay, that's what if give me the tennis ball again. Give me the tennis ball again. Yeah, get over your trap that you laid for me and give me the tennis ball. I don't know, just don't knock over my coffee cup. Okay, if I put a force on it, sure, its motion changes. But what if I put two forces on it from opposite directions?
You're gonna explode it.
No, I'm not gonna, because I'm not strong enough. But I'm putting two forces on it. Is there a force acting on it? Yeah. Why is its motion not changing? Because not every force causes a change in motion. Only, okay, come on. Oh, so these forces are balanced. So only what kind of forces cause change in motion? Unbalanced forces cause change in motion. And we'll talk more about that in the next chapter. Oh, by the way, if acceleration is velocity over time, what did we measure velocity in? What unit was velocity? Meters per second. And we divide that by time, measured in seconds. We end up with meters per second. How fast something's changing its speed is meters per second, which we sometimes abbreviate as meters per second squared. Acceleration is measured in meters per second squared. And let's not stop there. Why? By the way, what do we measure forces in? You remember? We'll just talk about the unit this time. We'll talk more about the math next time. How do we measure forces? Newtons. Yep, good. So you have two equations. Well, I guess really three, but two of them are very similar. Acceleration, you need to have this equation memorized and its units. Velocity, you need to have this equation memorized and its units. But it's effectively mathematically the same as speed, except this one also includes a direction. Do you have questions about the math? We'll do practice on the math tomorrow. Do you have questions about the concepts? We basically today talked about speed, which is a way of measuring motion, velocity, which is a way of measuring motion, acceleration, which is a change in motion, and forces, which cause changes in motion. Do you have questions? Did anyone take a note?